Welcome and thank you for joining us for today's webinar, Process Definition, Critical First Steps in the Validation of an EO Sterilization Process, sponsored by SteriPro Advanced Consulting Services and TechBriefs Media Group. I'm Sherry Trigg, Editor and Director of Medical Content with TechBriefs Media Group, and I'll be your moderator today. Our webinar will last approximately 30 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the presentation by entering it in the box at the left of your screen. Our presenter will answer as many questions as possible at the conclusion of the presentation, and those questions that are not addressed during the live event will be answered after the webinar. In order to view the presentation properly, please disable any pop-up blockers you may have on your browser. Our speaker today is Nicole Palick, a consultant on ethylene oxide for Sterigenics. Ms. Palick joined Sterigenics International in 2014 as a SteriPro consultant with a focus on ethylene oxide. She is responsible for leading and overseeing diverse, comprehensive analytical studies on medical device and pharmaceutical-based products and is well-versed in ISO standards and their requirements. She is also a lecturer on EO sterilization topics at Sterigenics seminars. At this time, I'd like to turn the webinar over to our speaker, Nicole.
Thank you, Sherry, and hello, everyone. Thank you for joining us today. Today, I'm hoping to teach you guys a little bit about the importance of process definition as it relates to your validation and why it's not only important, but it's also required. Now, on the agenda today, we're going to talk about what process definition is and why it is needed. I'll talk about the objectives of process definition. I'll provide you with some helpful tips. We'll summarize everything, and then we'll open it up for some questions. Now, what is process definition and why is it so critical? Process definition is often referred to as fractional work, and fractional runs are performed with reduced EO exposure time compared to what is specified in your sterilization process. So that EO gas flow time for your fractional runs is traditionally lower than what you see for your half-cycle gas flow time. Now, when you perform fractional runs, a lot of times other process parameters such as EO concentration and chamber temperature can also be adjusted. Now, ISO 11135 says process definition is the activity of obtaining a process specification which can be applied to the sterilization of the defined product during a validation studies. And TIR also goes in and says the goal of process definition is to establish a detailed specification for the sterilization process to be used in performance qualification, or PQ, of the defined product. So to kind of sum all that information up, it pretty much tells you that during process definition, you're creating the foundation of your validation. This is why it is so critical. In order to have a solid validation, you have to have a good base, and this is your process definition work. Now, some of the objectives we're going to look at during process definition are, we're going to determine your internal process challenge device, or PCD, through relative resistance. We're going to confirm BI appropriateness. We're going to evaluate an external PCD, and we're going to determine an appropriate EO gas flow time for your half cycle. Now, I'll go into more detail about each of these in the coming slides. First, we're going to talk about determining an internal PCD. You may be asking, so what is a process challenge device, or a PCD? You're going to hear that a lot. It is a device that's inoculated with a biological indicator. This could be a BI disc, a BI spore, or even liquid inoculum. And the BI is placed in the most challenging to sterilize location in this device. And this is to evaluate the delivered lethality of those process parameters. Where you decide to put that BI needs to be documented, both where you place that and the rationale for why you're placing it there. Now, to take it a step further, we're going to talk about what an internal PCD is. This is when you have that PCD placed inside the shipper case in the pallet. This internal PCD is what is used to validate your sterilization process, and it's done by confirming that the appropriate lethality or sterility assurance level can be achieved. Now again, documentation is very important. You're going to want to make sure you justify why you're choosing these internal PCDs, where you're placing that BI, and provide rationale for it. Now, how do you determine which is going to be your internal PCD? You're going to evaluate your product line to determine which device from that product line or from a specific product family represents the biggest lethality challenge. To do this, you're going to determine the hierarchy of resistance between the products in your product line. And this internal PCD is the device that you determine to be the most difficult to sterilize based on the product design and composition. Now, there's a couple of different ways that you can go about determining which device is going to be your internal PCD. You can use a paper justification option or a physical justification option, which would be your fractional run. For the paper justification, when would you use this option? A lot of times you use this option if you only have one device in your product line, or the devices in your product line are very similar and represent the same challenge to sterilization. So, for example, if you only have a product line of catheters or of tubing, you're going to want to look at those and you're going to want to see which one presents the greatest challenge. This could be a smaller inner diameter, which creates a more tortuous pathway for EO to travel, or the longest length of tubing. And this is going to be, the longer that length of tubing is, the more area that EO gas has to travel in order to reach the BI and get that kill. So you're going to have to look at factors like that. Now, based on this paper justification, you're going to have to, again, document everything. You're going to want to document, which devices you evaluated, why you evaluated it, and the outcomes of that. The more information you can add to this justification and these rationales, the better base that you're going to have and the better reasoning you can have to support this internal PCD that you chose. Now, the other option is a physical justification. And for this option, it's often used when your device or your product line contains different types of devices, such as a product line that has syringes, tubing, catheters, drapes. In this situation, it's hard to identify which one presents the greatest challenge because each device presents a different type of challenge. For example, the tubing that we talked about is that inner diameter and the length that creates the challenge, whereas for a syringe, it's the mated surface around the grommet. So in this type of situation, you're going to have to go a step further and you're going to have to perform fractional runs. Now, on this sterilization run or this fractional run, you're going to include different inoculated devices. Now, it's important that all these devices are included on the same run because you want to have them exposed to the same conditions. If you have them exposed to the same conditions, you can actually evaluate them against each other. If you don't have them on the same run and they see different parameters or different temperatures or different conditions, it's harder to justify that comparison. Now, off of this fractional run, you're going to look at the BI results and you're going to calculate the D values for each device and you're going to compare them to determine which one has the highest resistance. And this device that has the highest resistance is going to be your worst case and it's going to be considered your internal PCD. So now that we've got the first objective out of the way, let's go ahead and talk about the second one, which is to confirm BI appropriateness. Now, to confirm BI appropriateness, you have to demonstrate that internal PCD that we just talked about represents a greater or equivalent challenge to the sterilization process than the natural product bioburden of the product in your product line. And this is at the most difficult to sterilize location. So in other words, that spored product that you have has to be more challenging than the natural product bioburden on any device that you have in your product line. And this evaluation, again, is performed during fractional runs. And when you do confirm BI appropriateness with a specific internal PCD, that internal PCD is now referred to as the master PCD. Now, ISO 11135 presents 3 approaches to establish BI appropriateness. During this webinar, we're just going to touch upon approach number 2, because this is the most common and it's the industry standard. Now, for this fractional run, the samples that you're going to need are your internal PCD, which we talked about, that inoculated device that you determined to be worst case. You're also going to include your product sterility samples. Now, for product sterility, the device you use is going to be the device in your product line that represents the greatest challenge from a bioburden standpoint. And this is not only the quantity of bioburden, but also the type of bioburden. So, as you know, the different organisms present different challenges, so knowing this information is very helpful. You can also consider the challenge of the device when taking into consideration which device to choose. In other words, if you have 2 devices with the same amount of bioburden and one is a surface sterilization device and one has more complex design, such as tubing or a syringe, you're going to choose that tubing or the syringe because it has more of a challenge for the EO gas to get to that bioburden and get the kill. Now remember that the product sterility samples are not inoculated with a BI or any liquid inoculum. It's just that natural product bioburden that's on the device. You're also going to want to include the method suitability samples on the run, and the device used for method suitability is the same one used for product sterility. And method suitability is ultimately a validation test for product sterility. You're going to be inoculating that device with a known amount of organisms and then try and recover that organism. And the reason you do this is because you want to make sure there's no inhibitory factors on that device that would result in a false negative during product sterility. And so now that we move forward with the fractional run, some of the goals are you want to get growth on that internal PCD. You also want to get complete lethality or no growth on the product sterility, and you want to get growth on that method suitability samples after they're inoculated with a known organism. Now the thing to point out here is that you need to have growth on that internal PCD so that you can have something to compare to the product sterility. If you don't get any growth on that internal PCD, you don't have any data to compare to that product sterility samples. Now the results from this would demonstrate that that internal PCD is more challenging to kill than the natural product bioburden. And ultimately, it confirms that that internal PCD is an acceptable representative of your product line. Remember, you're using this internal PCD for your validation, so you want it to be representative of the actual products that are going to be sterilized. And then this internal PCD would be used for your performance qualification portion of the validation, which would be your half cycles and your full cycles. Now you may be asking, what if I can't confirm BI appropriateness with the internal PCD? So if you don't get the results that I just talked about, there are other options. You can create a more resistant internal PCD. Now this more resistant internal PCD, again, has to be equal or greater in resistance than your natural product bioburden. And some options here are to include different devices that may be more challenging or adjusting your device to make that device more challenging, such as taking your tubing and extending the length or decreasing that inner diameter so that that sample would be used for your validation. It would be seen as worst case. Now TIR 16 provides additional options should you not be able to confirm BI appropriateness, but we're not going to go into depth on those. Now just a reminder, when you do come up with this new, more resistant internal PCD, another fractional run needs to be performed to show or to confirm BI appropriateness with that new device. So now we've talked about that internal PCD, we've confirmed BI appropriateness, and now the internal PCD has become your master PCD. We'll move on to the third objective, which is to evaluate an external PCD. Now an external PCD is an inoculated device that's actually placed on the outside of the shipper box. This is different than the internal PCD that is actually placed inside with the product. Now this external PCD is used to monitor routine processing. And the reason that that external PCD is used instead of the internal PCD is it's a lot easier to remove that external PCD from the outside of the load. Now imagine a pallet of product coming out of a chamber. It's a lot easier for the operator to walk up to that pallet and remove that external PCD than it would be to open up those shipper cases, possibly break down that pallet, and get to the product inside to pull that and have it shipped out. Not only is it not, good for timing, but it's also unsafe for our employees. So a lot of times that external PCD is easier and safer. You're also not sending your own product in for testing. So you're not losing product that could have been released. Now oftentimes an external PCD is a device that's designed or built to be more resistant than your spored product or your internal PCD, such as like a test pack. Now how do you determine which PCD is appropriate? Again, you're going to want to perform a fractional run, and on this run you're going to include the internal PCD and you're going to include an external PCD. Oftentimes multiple external PCDs are used, and this is because they provide a wider range of resistance. So you're more likely to find the test pack that correlates best with that internal PCD. And again, that internal PCD needs to be equivalent or more resistant than the internal. Now when you perform these fractional to evaluate this relationship, you should be using a full pallet of material or dunnage. And the reason you're going to want to do this is because it represents what you're going to see during routine processing. If you take the device for the internal PCD and you take the device for the external PCD and you just place them next to each other inside of a chamber, they're not seeing the same conditions that they would be during routine processing, where that internal PCD would be inside the product and the external PCD on the outside. That change in where they're placed will change the characteristics and the resistance of those devices. So it's important to use that full pallet of material or dunnage for this comparison. Now on the fractional run, you're going to want to make sure you get growth on that external PCD, and you're going to need partial or no growth on that internal PCD. This would show you that that external PCD is substantially equivalent or greater in resistance compared to that internal PCD. Now, when you do this comparison, you don't always want to choose that external PCD that is significantly greater in resistance than your internal PCD. And the reason for that is, if you choose that PCD that's significantly more resistant, you may be challenging your process more than you need to, which could result in an extended, processing time, longer heat iteration. So you want to make sure it's at least somewhat similar in resistance with still being equal or greater. So we've just talked about a whole bunch of different types of samples, and I'm going to summarize them here. In the hierarchy of resistance, at the bottom you want your natural product bioburden. Again, that's that bioburden that just comes on your device through that manufacturing process. Next would be your inoculated product. This is the devices in your product line inoculated with the BI or the liquid inoculum. And then more challenging would be that internal PCD that you decided or that you found out through fractional work was the most resistant. And if you confirmed BI appropriateness, it's now your master PCD. And then at the top is that external PCD, which should be the most resistant and used for your routine process. Next, we're going to talk about that last objective, and that's to determine the gas flow time for your half cycle. Now, to determine the half cycle time, you're going to have to determine the D value for that internal PCD. Like I said previously, that internal PCD is what you use to validate your process. It's what you use to show that you can get the lethality that you need. So you're going to need that D value for the internal PCD. This D value is calculated from the fractional runs that you performed, and that data is then used to determine the minimum half cycle gas flow time. The D value definition is the time required to achieve inactivation of 90% of a population of the test organism under stated condition. Or in other words, the amount of time it takes to reduce that BI population by 1 log. So if you use a 10 to the 6 BI, going from 1 million CFUs down to 100,000 CFUs, the time it takes to reduce it by that 1 log would be your D value. Now in the definition, it's important to note that it says under stated conditions. That is, as those conditions change, that D value is going to fluctuate. If you have your internal PCD and you put it into a process that has a processing temperature of, let's say, 100 degrees, and then you take that PCD, the exact same one, and you put it into a sterilization process that has a temperature set point of 130, you're going to get different results. So you're going to get different D values. So remember, as you adjust those parameters, you're going to see variances in your D value. Also, when you do determine your D value, you're going to want to take that and you're going to extrapolate that out to determine the value or determine the gas flow time that you're going to use for your half cycle. Now, you're going to want to use the highest D value calculated during process definition. And the reason you do that is because, as I said before, the D value is going to change slightly as those parameters are adjusted. So as that changes, you want to make sure you're catching or you're representing that worst case condition so that when you move forward with your half cycle, you're actually covered. Now for that half cycle, you're going to want to get complete lethality or all kill on the internal PCD. And traditionally, a BI with 10 to the 6 population is used. So in order to get all kill on that BI, you need to reduce that BI population down to 0. Or in other words, you need to reduce that by 6 logs. So you take that D value that you calculated, you multiply it by 6, and you get that theoretical half cycle gas flow time. And that's the time that you should get all kill on your internal PCD. Now a more conservative approach is to use an 8-log reduction, and that's where you take the D value, you multiply it by 8, and you get the theoretical half cycle gas flow time. So for example, if you run your fractional runs and you get two different D values, let's say 5 minutes and 10 minutes, you're going to want to use that 10 minutes. And with that 10 minutes for a 6 log, you would have a gas well time for your half cycle of 60 minutes. Using 8 log, you're going to get an 80-minute exposure time for your half cycle. Now, when you're determining what time to use for your half cycle run, you need to take into consideration that external PCD. Yes, that internal PCD is what you base lethality off of, but you also want to make sure that you look at the D value for your external and make sure it falls within that range so that when you move forward with the half cycle, you can get the appropriate kill that you need, and then when you move forward with the full cycle, you can get all the kill that you need. And another thing to remember at this point is a lot of times this work is done in a developmental chamber or with a smaller pallet of product or one pallet of product. And when you upscale to your maximum load configuration of, let's say, 8 pallets, 12 pallets, or 30 pallets, you're going to increase the challenge of getting EO gas into the center of that load. So you're going to want to make sure you consider that when you actually set your half-cycle gas well time. So now we've gone over all the objectives, and I'm going to talk to you a little bit about some helpful tips during process definition. So first off, it may take multiple fractional runs to achieve this goal. This is common. You're trying to achieve a lot of different objectives, so if you don't have any historical data, it's very rare to only need 1 or 2 fractionals for this. It will take multiple fractional runs, and each fractional run is adjusted based on the results from the previous one. And then for process definition work, this can be performed in a developmental chamber. And a developmental chamber is smaller than your production vessel. Now, if you choose to do this, one of the reasons you would is because in that smaller vessel with that smaller load configuration, it's a lot easier to get fractional growth than, let's say, with a 30-pallet load, where that product is holding on to the EO and the heat, so it's probably going to give you more kill. If you do go with a developmental chamber, ISO 11135 does have some requirements, such as you have to have an IQ/OQ performed in that developmental chamber. It's the same thing that you would need for your production vessel. You also have to be able to show that that vessel or that developmental chamber can produce the same parameters and the same conditions that the production vessel can. You have to remember, you want this to represent your routine process. So if that developmental chamber can't provide the same parameters or the same conditions, you're not really representing what you're going to see during routine processing. Next is, you can actually evaluate the different objectives on the same fractional run. So for example, fractional run number 1, you can include the internal PCDs and the external PCDs. And as you get the results, you can compare the internal PCDs against each other to determine which one is worst case. And you can also just compare those internal PCD results to the external PCDs. Now you can also include product sterility, but traditionally, that product sterility isn't placed on a fractional run until you have a better idea of what gas well time is going to give you fractional growth. If you're starting from scratch and this is your first validation with this product, you may not know at what gas well time is going to give you fractional growth. So for fractional 1 and maybe 2, you're trying to find that optimal gas well time to give you that quantitative growth on the VIs. And then once you achieve that next fractional run, you can go ahead and include product sterility samples. And that's because now you're more confident that that run is going to give you the results on the internal PCD so that you can compare it back to the product sterility. Also, if you don't get the desired results on your fractional run, you can adjust those parameters for the next run to increase the likelihood of you getting the results that you need. Now remember, as you adjust the parameters in process definition, it does not mean you're adjusting the parameters in your half cycle and your full cycle. In the fractional, you're doing the objective of getting that growth. So you're adjusting those parameters and able to get that growth to do that comparison. You don't follow that through with the half cycle and the full cycle, because with those, you're using your actually proposed cycle parameters to get the kill that you need. And then finally, during process definition, we've talked about using multiple PCDs, such as internal PCDs, external PCDs, and multiples of each type. However, when you move forward with the performance qualification or your half cycles and your full cycles, traditionally, you only use 1 internal PCD and 1 external PCD. Now, to summarize everything that we've kind of talked about, is process definition is a critical part to the validation process. There are several objectives that you're going to want to look at, and that's determining your internal PCD, confirming BI appropriateness, evaluating the external PCD, and calculating that half-cycle gas flow time. And finally, that process definition is a very complex process with a lot of moving parts, so it may take time to achieve the results that you want for each objective. So that brings us to the end of our webinar, and I want to thank you guys, and we'll go ahead and open it up to some questions.
Thanks, Nicole. At this time, we will begin our Q&A. If you have a question, remember you may submit it by entering it in the box at the left of your screen. So Nicole, our first question today, how do you determine which device is worst case from a bioburden standpoint for product sterility testing?
So in order to determine which device you should use for product sterility, it's always recommended that you do bioburden testing on those devices. That'll give you an idea of not only the quantity, but the type of bioburden on those devices. In addition, you can actually look at the devices, and usually if they're the same device through the same manufacturing procedure, and if one has more surface area, such as a larger tubing than the other, a lot of times that larger surface area will present more of a challenge for bioburden. However, we always recommend that you back it up with bioburden testing. It just bolsters your argument for which device you're choosing.
Thank you very much. Okay, so our next question, do you have experience in BIs being in place in a location other than the most challenging location, something our sterilizer have suggested we look at?
So it's always a good idea, and the standard actually supports this as well, that you place kind of internal PCDs or BIs throughout the load. And the reason you do that is because you want to make sure you're challenging every part of that load. It's important to make sure that that BI is placed in one of the most challenging locations, but by placing it throughout, if there's a cold spot in the chamber, you're going to capture that. So you want to make sure that you characterize the entire load and place them throughout the load.
Thank you. Our next question, when you get growth on your product sterility test, can you compare D-value of your IPCD versus the D-value of your natural bioburden?
So the standard actually has, in the approach that we've been talking about, it actually says that you have to get complete inactivation of your product bioburden or your product sterility samples. The other issue with doing that method is a lot of times your bioburden is not very high. So it's usually at 50 CFU, 100 CFU. That BI is up in the millions. So when you calculate that D value, you're going to get a very stark difference between the two. So, in addition to that standard requiring you to get the kill, even if it didn't, that comparison would usually not work.
Thank you so much for that answer. Our next question, do you have to requalify EPCDs, and if so, at which frequency?
So it's a great question. Once you establish your external PCD during your process definition work, that is the device that you use for routine processing and for your future requalifications and any other studies such as product adoptions or anything like that that you're doing. Now, if you have a change in your product line or a change in your sterilization process parameters or your load configuration, then it's always a good idea to reevaluate that external PCD to make sure that it's still comparable to possibly that new product that you're bringing in or that new parameter change that you have. Because changing parameters could adjust that relationship between the internal PCD and the external PCD.
Wonderful. Thank you again so much. So our last question that we have time for today, let's go ahead and go to, you mentioned considering future load sizes when performing the validation, for example, initially 1 pallet, later 5 or 9 pallets, et cetera. What steps can you take initially so that revalidation is not necessary?
So a lot of times during process definition, one of the things that you may consider performing is a simulated half cycle. Now this simulated half cycle doesn't actually go towards your validation. It can be performed in that pilot vessel, but you run it with the parameters that you're looking to run for your performance qualification half cycle. And that gives you an idea of if you can get kill on that, it'll give you a better idea. So when you're determining that minimum gas flow time, it's always recommended that you kind of take additional logs into account. You're going to want to look at the different, like the upscale of the load. If you're going from 1 pallet, let's say, to 30 pallets, or 1 pallet to 8 pallets, it's all going to be on a case-by-case basis.
Thank you, Nicole. And with that, we are at the end of our webinar. If we did not have time to get to your question, they will be answered after the presentation is over. I would like to thank Nicole for this discussion today and thank our audience for being with us. A survey will pop up on everyone's screen immediately following our program. Please tell us what you thought of our webinar by answering its 5 short questions. This webinar will be archived and available for viewing on our website, and an email will be sent to everyone who registered for today's program as soon as the archive is ready. I'm Sherry Trigg with TechBriefs Media Group. Thank you again for joining us.